It's been said that what goes up must come down, but I'm not so sure that's true. Let's do a thought experiment. Imagine throwing something vertically upward from sea level. You give it enough velocity, the object can rise pretty high. But yeah, I suppose gravity's going to do work to decrease the object's kinetic energy, make it reach zero at its apex, and come back down and crash into the earth. But what happens if you throw it with greater velocity? Well, then it's just going to rise higher, but still come back and crash into the ground. Is there a limit to this behavior? Can I throw something fast enough that it rises and never comes back down? The answer is yes. And the minimum velocity required to make this happen is often referred to as the escape velocity. Escape velocity depends on how massive the object is that you're trying to escape from. So for us, we're probably most concerned with the escape velocity from the Earth, but every planet, every moon, every star, every celestial body has an escape velocity. The escape velocity is also a function of the starting point. To get an object to escape from the surface of the Earth would require greater velocity than to get it to escape if it was already at some higher altitude h. But let's deal with the escape velocity from the surface of a planet for starters. We could apply the law of conservation of energy in an attempt to investigate how large the escape velocity would have to be. So how about this? We'll say that the object leaves your hand with some initial kinetic energy due to the velocity you give it to start with, and it has some negative potential energy because potential energy is only equal to zero, infinitely far away. So let's just say we do throw it fast enough that it can rise and never stop. Now, there's not enough room, so we'll do a scale break and imagine that we can actually get to a point of r equals infinity. Well, by definition, at that point, gravitational potential energy has to equal zero. So there's a point A when the object leaves your hand, and there's a point B when the object finally gets infinitely far away. At point A, it has a kinetic energy of 1/2 mv squared, and it also has a gravitational potential energy equal to negative g(mm) over r. Now, if we're saying that it just barely makes it infinitely far away, then we're saying by the time it gets infinitely far away, its kinetic energy has just reached zero. And this is kind of hard to wrap your head around, right? We're saying that it reaches zero when it gets infinitely far, then doesn't it turn around and come back? So this will maybe challenge your concept of infinity. But in any case, we have a combination of potential energy and kinetic energy at point B, and a combination of kinetic and potential energy at point A, and the total combined mechanical energies should be equal because gravity is a conservative force. So if we set the energy at A equal to the energy at B, then we have 1/2 mv squared minus gmm over r is equal to 0. This means that 1/2 mv squared has to equal gmm over r. And as we've seen so many times in this unit of study, the mass cancels out, and we have v is equal to the square root of 2gm over r. That's interesting. We'll call this v subscript ESC for escape velocity. Let me put a bubble around that. We found earlier that if I want to put this thing into orbit instead of make the object escape, well, orbital velocity, we'll call that VT, tangential velocity, is equal to the square root of gm over r. Very similar, just in one case, there's a 2. So in other words, we could say escape velocity is the square root of 2 multiplied by orbital velocity. Well, if we want to find the escape velocity from the surface of the Earth, then we should change the lowercase r into a capital R. And then we'd say that's the same thing as the square root of 2 times the treetop orbit. So let's see what that happens to be for the Earth. The square root of 2 times 6.67 times 10 to the negative 11th times 6 times 10 to the 24th divided by 6.4 times 10 to the 6th. That all calculates out to about 11,183 meters per second, or if you prefer, 11.2 kilometers per second. Not kilometers per hour, kilometers per second. But I do remember that the speed of a treetop orbit is about 7,900 meters per second, or 7.9 kilometers per second. Well, do a quick check. Multiply 7.9 kilometers per second by rad 2, and you should get 11.2 kilometers per second. An interesting thing about escape velocity is it actually doesn't depend on what direction the object is projected. Now, if you throw something straight up with a speed any less than 11.2 kilometers per second, then the statement, what goes up must come down, holds true. At a speed of maybe 10.9 kilometers per second, the object's going to rise terribly high, but it won't get infinitely far away before it reaches a speed of 0, and therefore turns around and comes back down and crashes in, and the path it follows would be a straight line. What if I projected something from Newton's Mountain? Let's take a return visit to Newton's Mountain. So if I project something too slow, crashes into the Earth. A little faster, still might crash into the Earth. If I can give a tangential velocity of 7.9 kilometers per second, that's the one perfect speed that makes the object fall around the Earth as opposed to into the Earth and achieve a circular orbit. Now, if you throw it faster than that, then it doesn't get away and escape the Earth. Although it doesn't follow a circular path either, it takes an elliptical path and returns back to the throw. But what if you increase the velocity so much that it goes up to 11.2 kilometers per second? Then it travels farther away and farther, and the radius continues to get farther and farther, and it would spiral outward and never form a complete bound orbit. So, escape velocity is not a function of the angle at which the object's projected. It just depends on the value of the velocity. What's the escape velocity for a geosynchronous satellite? Escape velocity is the square root of 2gm over r. The value of r for a geosynchronous satellite is about 6.6 times the radius of the Earth. So v would be equal to the square root of 2 times 6.67 times 10 to the negative 11th times 6 times 10 to the 24th divided by 6.6 times the quantity 6.4 times 10 to the 6. Ooh, a lot of sixes. Okay, v is the square root of, grab your calculators, this is the square root of 2.02 times 10 to the 8th meters squared per second squared, which comes out to about 4,500 meters per second, or 4.5 kilometers per second. So escape velocity is not a singular value. It depends on your starting altitude, but often what we mean by escape velocity is the escape velocity from the surface. So one last time, in general, there's the equation for escape velocity. If we want escape velocity from the surface, then it's the square root of 2 gm over capital R.